This video was designed to help you understand basic medication dose calculations for the pediatric patient. Unlike adults, medication doses are calculated based on a child's weight in kilograms. Because math is required to calculate the correct dose, let's review basic math principles. Any whole number can be made into a fraction by putting that number over 1. When the number above the division line, the numerator, is the same as the number below the division line, the denominator, the fraction equals 1. By multiplying any number by 1, the answer is the same number. The answer matches the original number. Therefore, using a fraction that has equal value on the top and bottom is like multiplying by 1, as shown in red. Multiplying by several ones, or fractions that equal 1, will always give you an answer that matches the original number. When multiplying fractions, any numerator can be crossed out with any similar denominator. The 8s are crossed out in green, the 5s are crossed out in blue, and the 4s are crossed out in red. The answer is 3 over 1, which equals 3. Just like numbers, measurement indicators in the numerator can be crossed out with similar measurement indicators in the denominator. Pounds are crossed out in blue, leaving the answer in kilograms. Now let's apply these principles to calculate a medication dose. A child who weighs 24 pounds 4 ounces has been ordered amoxicillin. A safe dose for the indicated use of this medication is 15 milligrams per kilogram every 12 hours. What dose will you give the next time it is due? Round to the nearest tenths. First, let's determine what information is important to answer the question. What is the question asking? It is simply asking for the dose for the next administration. The frequency, every 12 hours, is not necessary for answering the question. To calculate the dose for the next medication administration, you will need to know the child's weight and the dose-weight ratio. Because there are two indicators in the weight, pounds and ounces, we will need to convert the weight to pounds only first. 32 pounds 4 ounces is not the same as 32.4 pounds. 0.4 is 4 over 10. 4 ounces is 4 over 16. There are 16 ounces to a pound. To change ounces to pounds, we will start with 4 ounces, placing it over 1 to make a fraction. To multiply it by 1, we will use the fraction 1 pound over 16 ounces. 1 pound of sugar is the same weight as 16 ounces of sugar. Equal values on the top and bottom are the same as 1. The ounce value needs to be on the bottom, the denominator, in order to cross out the ounces and be left with pounds. Therefore, we will write the fraction as 1 pound over 16 ounces and not 16 ounces over 1 pound. Both ways equal 1, but only the first way will help us solve the problem. By crossing out ounces, we are left with the desired indicator, pounds. Now we simply multiply across the top and multiply across the bottom, and then divide the answer to change it to the decimal form. 32 pounds 4 ounces equals 32 and 25 hundredths pounds. Now we can set up our math problems starting with the child's weight in pounds. 32.25 pounds is placed over 1 to create a fraction. Then we multiply that by 1 to get a value that matches the original number, just with a different indicator of measurement. The fraction that equals 1 is 1 kilogram over 2.2 pounds. The pounds value is placed on the bottom so that the pounds can be crossed out, leaving the desired indicator of kilograms. We simply multiply across the top, multiply across the bottom, and divide that answer to receive 14.659 kilograms. Now that we have our weight in kilograms, we can do another problem to multiply the dose-weight ratio. To simplify the process, though, instead of multiplying out our answer, we can add another chain to our problem. Add another 1 to continue changing the indicator to the desired indicator of milligrams. To answer the question, we need the dose in milligrams. Now we're going to add another 1 by using the dose to weight ratio, 15 milligrams to 1 kilogram. We place the kilogram on the bottom to cross out both kilograms, which gives us our desired indicator, milligrams. If the question would have asked for the dose in grams, we could add another chain, another 1, using grams and milligrams. 1 gram equals 1,000 milligrams. For this problem, the red pounds will cross out as well as the blue kilograms, leaving us with milligrams. We will multiply across the top, multiply across the bottom, and then divide that fraction to get an answer in a usable format. The question asked us to round the answer to the nearest tenths. Because the hundredths value, the second 8, is 5 or higher, we will round the value in the tenths column, the first 8, to 9. This will give us an answer of 219 and 9/10 milligrams. When you calculate medication problems, always remember to include the indicator with the numerical answer. This will ensure proper administration of the medication. In review, we started with the child and ended with a medication dose that matched the child. By starting with the child's weight and then multiplying fractions that equal 1, we were able to calculate the correct medication dose for that particular child, ensuring a safe medication administration.